Okay, let's continue our talk. This time, our topic is Kolmogorov-Smirnov goodness of fit test. This test is actually abbreviated KNS test. Okay, taking the initials of these letters. These are two people from a mathematician from Russia. So name is Russian name. Okay. Then we have data. This is the data about fasting blood glucose values. We're taking from 36 non-obese, apparently healthy adult males. Okay, here 36 data. So here we just want to check whether this data excuse me, follows a normal distribution. Okay, and this is the mean value is 80 and the standard deviation is 6. I just want to check this variable really follows normal distribution with this mean value and this standard deviation value. Okay, let's look at the table first. First of all, we have to look at the frequency distribution for the data, 36 cases here. So lowest value is 68. We have 2 cases, and second one is 72 cases, and 2, and this is etc. So we have adding about 36. So based on this one, we have checked the cumulative frequency, okay, 2, 4, 6, blah, 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 okay? Then we transform into we calculate the probability, frequency probability is the lowest one is for the 68, x value is 68, then the probability is 0.0556. The second one is 72, is a 0.1111. Okay, so actually this is the probability for the cumulative frequency. This is also frequency distribution up to 1. Okay, that's the data f of s. S means the sample data. Okay, then if the data lay out like this, then what if we apply this value into normal distribution? What it would be? So in that case, we have to transform this value into z to get the normal distribution probability. So since we know what is the mean value, what is the standard deviation, mean value is 86, excuse me. Okay. The mean value is 80, the standard deviation 6. When do you remember standardization formula here? So all the x value is put here, then this x value is transformed into z. Okay, so they end up with minus 2.00. For the 72 is minus 1.33. In this way, we can calculate all the z values here in this column. Okay, those are z values. Then based on this one, we go to the standard normal distribution table. And up to this point, we can calculate what would be the probability here. Okay, also it's going to be a cumulative distribution. Okay, then, okay, when we compare these two distributions, the difference is like that. So here, the largest difference is, biggest difference is seen here. Okay, my 0.1547, the probability difference, right? Okay, then we move to the next slide. Okay, then we have to look at the table M. So decision rule is reject H0 if the computed value of D is exceeded 0.221. The critical value of D for n equal to 36, alpha is 0.5. So based on this one, we calculate the test statistics. Okay, then we see the graph here. So this is this graph is a line is actually under the normal distribution, cumulative normal distribution curve, and we call it the step function because we have probability for the sample data. probability of here is 68. Okay, lowest value 68, and this way all the values here. So the probability we have calculated, okay, on the first the sample data probability series. This is the dot is the value. Okay, so when we actually the first category was 68, second category was 72. So until we reach the 72, the same probabilities continues, and we reach the 72, so we have new probability. Okay, so here the dot is here, and the next is 75. Until we reach the 75, this probability continues. That's why it looks like this, not like this line here. Okay, so we cannot draw this line because we have to calculate every probability, the probability at every point. Okay, so in this case we are looking at difference. This D is 1.16 was the largest difference. Actually, it was well, not exactly 0.16, was 0.157, something like that. Okay, so that is the part that shows the largest difference between sample distribution and the theoretical distribution. So here, okay, then we move to the next slide. So what is table M? Table M looks like that. So here in the for the headings of this table is one side test and two side test. So sometimes we conduct one side test and two side test. So based on this one, there's a probabilities lies here. Then where's the sample size of 36? Okay, here the sample size is 36. Okay, then here is the 36. Okay, 36. Then here the value is here. There's the point probability is here up to 90%, 95%, 98%, 99%. So when our value is located here, okay, outside the 5%. So our alpha is 5%. Is above the 5% here. Then when that value belong to here, then it's gonna be significant. Okay, so calculate this one. So this one series when we mark 90% from this graph is minus 0.174, so 95% to 199 and 98% to 221. Okay, so when we reach, so when our value for the sample size 36, the point is the difference probability sorry, probability difference is 0.221, then it's gonna be probability would be 98% for two side test. For one side test, it's going to be 99%. Okay, so but our calculation value, okay, so for the 95%, if my probability is exceeding this 0.199, then at the alpha is 0.05, that's actually critical value. Okay, but where is my value? My value is 0.1547. Where does it locate? It locates somewhere here. Then inside the 90%. Okay, so in that case we fail to reject the null hypothesis. So in that case we can say this probability, what is value means? We have to accept the null hypothesis. Null hypothesis. What is the null hypothesis? Two probability distribution is same. So in that case, since our value is located here, so we can say this data, 36 people's data, follows normal distribution. That's our conclusion. Okay, here, so the test statistic D may be computed algebraically. We calculate this one. So here, as I said before, our D was okay, almost 0.96, 9.6 located inside here. So exact value is -1.1547. So we cannot reject. So inside inside beyond the probability level, So we can say this is the we are unable to reject null hypothesis. So here 0.5, so p-value is greater than 0.2. That's the checking for normal distribution using Kolmogorov-Smirnov one sample test, something like K and S test. Okay. Here, when this computer output, there's another special the software StatSect. Okay, then we have sample data and probability data, and the sup means biggest value, supremum. Okay, biggest value. What is that? So the observed statistics was 0.106. Okay, stand for the statistics is the p-value is approximately this one. Okay, so it means exceeding 5%. So we are unable to reject the null hypothesis. Okay. Then this one is the reverse side, f of x minus s of x. Okay, so actually same thing. So through using, so even though we didn't calculate the probability everything, but when we look at this computer output, you can figure out whether we can reject or not. Now then we move to the Kruskal-Wallis one-way analysis of variance by ranks. So this is kind of one-way analysis of variance in parametric method, but here we have data. We have three groups here: air, benzaldehyde, and acetaldehyde. Okay, this is a case of the pulmonary effect of a guinea pig. It's experimental animals. So they expose the ovalbumin, ovalbumin sensitized guinea pigs to regular air, the benzaldehyde and or acetaldehyde. At the end of the exposure, the guinea pig was anesthetized and allergic responses were assessed in bronchoalveolar lavage, okay, BAL. One of the outcome variable examined was the count of eosinophil cells, a type of blood cell, white blood cell that can increase with allergies. So this is table shows the data. Okay, it's actually measured 10. The measures unit is 10 to the power of 6. Okay, for the three treatment groups. So here, whether there's we have three groups here, then is the equal or not. Okay, that's our question. Now, then, what is the Kruskal-Wallis procedure? So Kruskal-Wallis procedure is actually we have sample size from N1 for the first group and 2 for the second group, something like that. So from K samples, it's combined together, and in a single series of size n and arranged in the order of magnitude from smallest to largest. The observations are then replaced by rank, okay, from 1 to the which is assigned to the smallest observation, and then n is assigned to the largest observations. When 2 or more observations have the same value, tied value, then each observation is given the mean of the rank for which it is tied. It is the same thing we did before. Okay, the second is ranks assigned to each observations in each of the K groups are added separately to give K ranks. Okay, then we have tested the statistic here. We have this one is a rank, sum of rank. Okay, then J is a group. If J is 1, then first group's ranks, sum all the ranks, then square the value. Okay, then divided by sample size and minus 3 multiplied by total sample size here. Then we can calculate this one very easily, not difficult. So the test statistics we say this is H. Okay, this is K is the number of samples, and J is the number of observation in J's sample. Okay, then N is total sample, and Rj is the sum of the ranks in the J sample. Then there are 3 samples, so 5 or fewer observations in each sample. The significance of the computed H is determined by consulting appendix table N. There's also another table. So when there are more than 5 observations in one way or more of the samples, H is compared with the tabulated values, the chi-square value. Is an interesting thing is we go to where the sample size is 3 samples, then we look at table N. But with sample size exceeding 3 or 4 or 5 something, then more than 5, then we go to the chi-square test. Okay, testing method is different. Okay, then let's go back to our sample. So data is explained. What kind of data? We have explained it already, and with some assumption, the samples are independent. Independent random sample is very important. So groups are not related from the respective population. All the population is different, so that they must be independent. The measurement scale employed is at least ordinal, okay, rank. If they are measured in numeric data, then it should be transformed into ordinal. The distribution of the values in the sampled populations are identical except for the possibility that one or more of the populations are composed of values that tend to be larger than those of the other populations. So here we have a hypothesis here. The null hypothesis, population centers are all equal. It means since this is a non-parametric approach, we cannot talk about the mean value. Only thing is where this is located. So when there must be a center, even though their population distribution is weird, there must be a center. So we regard if the 3 population centers are all equal, that it means equivalent to the all means are same. Okay, and the alternative hypothesis, at least one of the population tended to exhibit larger values. I mean that the center is not located in one side. At least one is away from the other 2, then we are going to reject the null hypothesis. Here, alpha is 0.1, so test statistics. We do remember the equation, okay? The H calculation equation, that's the test statistics. And distribution of the test statistics, the critical values for H for various sample sizes, and alpha is given in table N, okay? Then decision rule, when the computed H value is exceeding, okay, so the critical value, then we have to reject the null hypothesis. Okay, then calculation of statistics is done through the H calculation formula. Okay, then we have to decide what's going to be. So here we have 3 groups, okay? 3 groups here. So actually original table had each individual case has their own value. Based on this one, we put order. Among 36 cases, this value is the lowest one. So he got the rank is 1, okay? And second one is the largest value is also here is 15. We have 15 cases, right? 15 cases. Not 30, 36 is before the Kolmogorov is one of test. I'm sorry, I'm a little mixed. The sample size is 15. So rank lowest value would be 1, highest value 15. So this one is the lowest one, second lowest one, third lowest one, fourth lowest one, then move to here, fifth the lowest one. And the sixth here, and seventh here, eighth here, ninth here, blah, blah, blah. So after we put all the ranks here, we're adding all the ranks, okay, for the first group, and second group, and third group, okay? So we have 3 ranks. Now then we look this one for the first group, rank sum of rank. This one second group, for the third group, So we calculate this very simple calculations. So we got the value is 9.14. Sent this decision here. So we have to go to table N. It's a sample size all 555, 3 groups, and we calculated H value is 9.14. Then what would be the probability value for this H? Okay, so if the dejection level is 0.4 or alpha is 1%. Okay, then conclusion. Now then let's look at what the table is label N here. This is sample size, okay? So N1, N2, N3. So when the sample size is first sample size is 2, and second sample size is 1, the third sample size is 1. Then we go to this way. But what are our sample size? 5, 5, 5. So we have to move to not in this table. With the next page, we see that this one, 5, 5, 5. Okay, 5, 5, 5. And here we have a probability series here is up to 8 points. So the value is 8 points. Then the probability would be 0.009. So when we move up to, since what we say, we had the alpha level is 1%. So this is the mature. So this value, okay, if this value is exceeding 7.98 is alpha is 1%, is going down, so the values go down, then what's going to be? The probability decrease. Okay, so whenever our calculation value locates here, then it's going to be significant. But it's going up here, then probability is increasing, so it's not significant. Now, what was our H value? 8. Okay, 8 located here, slightly passing this line. So when we say, what we can say is that the 3 groups central location is not equal difference. Okay, so this one is here. We can say the significance. What if we have a tide value? Okay, what if we have tide value? So here, when tides occur among observations, we may adjust the value by h by dividing it by this one. Okay, here t is equal to t3 t cubic minus t. Okay, the letter t is actually to designate number of tide observations in a group of tide value. In our example, there are no groups of tide, so you don't have to worry about it. Okay, that's the Kruskal-Wallis test. And when we have 5 groups here, well, not 3, okay, it's up to E is 5 groups. Then we do the same thing. So this is the money data, okay, so value of equipment per bed by hospital type. So we have 5 hospital types, A, B, C, D, E. Then among them, we have the money, okay, net book value for this one. So how we don't care how this money data is calculated. Anyway, based on this data, we put rank, okay? The cheapest one is this one, okay, the number 1. The second, this one. And how many cases we have here? We have to calculate. Okay, here the up to 40, what is the highest rank? Maybe this one, 41. It's 41 here. This one seems to be the highest rank. Anyway, all this data is ranked from lowest one to the highest one. Then we sum all the ranks here, R1, R2, up to R5, okay? Then with this one, what we do put this one, okay? At the previous example, we have 3 groups, but here we have 5 groups. Expand to the 5. Then all the others calculation procedure same. So H is 36.39. Okay. Then the degrees of freedom is here. K, we have K group. Since we are moving to chi-square distribution, we have to think about the degrees of freedom. So we have 5 groups, K minus 1, 4 degrees of freedom. Okay. Then this one, so we check whether this value is located. okay, then we can determine significance. This is a chi-square distribution, okay. So degrees of freedom was 4 here, okay, from this one. So the based on this one, this may be the 4 is alpha is 5%, then 9488 is the significance level, and is 1%, then this one is the significance level. But our calculated value exceeding this one, so we can say this is significance. Okay. Now here, so the degrees of freedom is 4, is a more big letter. Okay, so the 9, this one for the 1%, this one is a 5%. So our calculated value is obviously exceeding this one. Here, the H value is not 9.1. There's a degree of freedom 2, and P value is 0.01. So we say this is significance. All groups are not same. Okay, that's what happened. Now we move to the Friedman two-way analysis variance. Okay, it's also by rank. Here, a physical therapist conducted a study to compare 3 models of low-volt electrical stimulators. 9 other physical therapists were asked to rank the stimulators in order of preference. A rank of 1 indicates first preference. The results are shown in table 13.91. So we wish to know if we can conclude the models are not preferred equally. So here the physical therapist is using the machines, okay, the machine, and there are three models: A model, and B model, and C model. In this case, we don't know which one is the best one. So it depends on, according to a different therapist, preference would be different. So we picked up the 9 therapists, okay? 9 therapists. For each therapist, asked to use 3 models altogether and put the rank. What is the best one? What is the lowest one? So I don't know how it is. The rank of 1 indicates the first preference. The best one is 1, lowest one is a 3, the middle is a 2. So all different therapists put different rank. Okay, so in that case, how can I determine? Okay, if for example, every therapist put 1 here, and second, this were 2 here and 3 here, then everybody ranks like that. Then obviously C is the best one. So because 9 people, it says C is the best one. Then C must be the best one. So here somebody put 2 here, somebody put 3 here, somebody put 2 here. Also the other guy puts 2 here. This is a little bit confusing. So we have to check whether there's a pattern, okay, is how different they are. Okay, then solution. So that there's the data is a table, the previous table, and our assumption is the observations appearing in a given block. Okay, here there's each individual therapist regarded as a block. Okay, first block, first people, the decision, the 1 to 3 decision is not related with the other the therapist. So in that case, the therapist regarded as a block. So the control them by block. Okay. So and within each block, measurement at the least ordinal scale achieved. So within each block, within each therapist, we put 1 or 2 or 3. Certain hypotheses. In general, the hypotheses are the null hypothesis for our treatment have all identical effects. That means everybody agrees, okay? But at least one treatment tend to yield large observations than at least one of the other treatment, okay? So for our present example, we state the following as follows. 3 models are equally preferred, and the alternative is not equally preferred. Okay, so alpha is 5%. Now we move to here. So we have to find out the test statistic. Whenever if we select statistical test, then we look for what is the test statistics. We have to follow. We have to determine what the formula is appropriate for this statistics. So that's what we call statistics. Every statistical method has a test statistics to evaluate the significance. Okay, by means of a Friedman test. So in that case, Friedman test actually two-way. So the rank is 1, 2, 3. Okay, 3 different the stimulators, okay, models. Okay, and the therapist is kind of blocked. So blocked design. Okay, not factorial design. It's blocked design. So that's the Friedman test. So by means of Friedman test, we will be able to determine if it is reasonable to assume that columns of the ranks have been drawn from the same population. Okay, if a null hypothesis is true, then we do expect to observe the distribution of rank within any column of 2 with result of the chance factors. The chance factor result of the chance factors, and hence we do expect a number 1 to 3 to occur with approximately the same frequency in each column. So all the ranks are mixed up. Okay, so it's in other words, rank sum is same. If the suppose rank sum is same, so all 1 to 3 is mixed up in each models. Okay, so that we have sum of rank are same in 3 groups, then obviously we have to accept null hypothesis. But if it's skewed to some other, the ranking is skewed to some other models, okay, specific models, then this must be not the same with the other models. Okay, so that's what it says. So if on the other hand the null hypothesis is false, okay, it means the model is not equally preferred. Okay, some specific model is more preferred by a therapist. Then we have to reject the null hypothesis. So we'd expect the preponderance of relatively high, okay, rank at least 1 column. This condition would be reflected in the sums of the ranks. Okay, then Friedman test will tell us whether or not the observed sums of ranks are so discrepant then that it is not likely they are a result of chance when H0 is true. The sense data already consist of ranking. Okay, it's already, we don't have to worry about ranking because every therapist put 1 to 3 ranks there within blocks. Okay, with rows. This is row. Our first step is to sum the ranks within each column. Okay, so it is actual treatment. So different groups, okay, different models. These sums are Rj as we did in the Kruskal-Wallis test shown in table 13.9.1. So test statistics by Friedman test is, we call it chi-square sub R. Okay, then this is nothing but a notation to differentiate from the other chi-square value. So this is the formula. Okay, then Rj is the sum of the ranks in each group. Then that get the squared value, so minus 3n multiply k plus 1. Okay. Then what is the n? N is the number of rows. Okay, how many therapists are there? And the k is the number of columns treatment. I mean the models. So we have 3 models. Okay. Then we use this formula. It's very easy to calculate. Then based on this one, the distribution of test statistics, we can find the critical values for various the values for n and small n and k as a given table O. So when go to the table O, you have to bring the number n and x, k. Okay. So then reject null hypothesis if the probability of obtaining when H0 is true, the value of chi-square is larger than actually computed is less than or equal to alpha. So let's calculate the test statistics. We put the sum of the ranks for the first group is 15, second one is 25, third one is 14. So we get the squared value and adding up together. This calculation formula is very much similar to the previous one, but anyway, it's a little bit different according to somewhere there's some difference. So all the statisticians who developed this method is adjusting the situations. They based on the same form as a calculation formula. So according to different method, the formula shows a little bit different. Okay, then the chi-square R sub R is calculation 8.222. So then we go to the table OA. When you go to table OA, you have to bring the number N and K. So what is K? K is 3. N is 10, right? Here like this. So when the based on this one, when maybe the critical value is 0.016, okay, 0.1066. So we are able, therefore, to reject null hypothesis. Conclusion here, p-values here. Let's go to the tables here. What does the table looks like? Table OA. It is a very little bit complicated formula, but n is equal to 2 and 3, 4, 5, 6, 7, 8, 9. How many therapists do we have? 9 therapists. Okay, n is equal to 9 here. Okay. So this letter is too small, so it will expand it to more visible situation here. So our our calculation was 8.221, 2222, okay, 8.222. That's the H value. H value located here. The H value gets a smaller value, okay, gets a smaller value, then it's going to be the probability is increasing, okay. In the lower value, it becomes significant. So the value is the following this point, okay, then so we can say this is significant. Okay, based on this one, so we look at this the table here. So our calculated chi-square value is 8.22. Okay, then degrees of freedom is 2 because group is 3. So k minus 1 is degrees of freedom 2. Then probability is 0.017. Okay, it means what? It means the probability is too low. So that we can say that maybe at alpha is, if alpha is 1%, then we fail to reject this one. But if alpha is 5, then we're going to say it is significance. Okay, that's it. Then we have large samples. When the value of k and n or n exceed those given in table O, okay, table O is the maximum value was 9 in the table. Anyway, from this table O, the value is exceeding, then we go to chi-square distribution table, table F. Okay, so here the example 13.92, the table 13.92 shows the response and percent increase in cell body flow. That's another data of 16 experimental animals following different dose levels of atropine. The ranks in parentheses and the sum of ranks are also given in the table. We wish to see if we may conclude that the different dose levels produce different responses. That is, we wish to test the null hypothesis of no difference of response among those levels. Okay. Here we have the data here. We have 4 groups. Okay, 4 groups, and animal number is 16. Okay, so this value is taken from the animal percent increase in cell body flow of experimental animals following different dose levels of atropine. So we have atropine level is 1, A, B, C, D, all different levels, okay? All different levels. Then check the ciliary flow as a percent decrease, okay, by applying those levels, okay. Then there's all the data here. So here it is animal. Each animal is applied with a different dose. Then this animal shows 29 for A and 48 for B, 75 for C. Then for the dose level D is 100. So based on this one is the lowest one, and the second one, third, fourth in order. Okay, that is the result for animal A, animal 1, and obviously this one works as a block. Okay, so then second animal, we do the same thing. Okay, so here there's the 100 as a tide value here, so it should be either 3 or 4, but since they are equal value, so this was 3.5. This rank is written as 3.5. And say the same way with 16 blocks, okay? Put each rank here, then we're adding some the rank here. For the first group, and second group, and third group, and fourth group. If this rank is the same, okay, it means then the ranks are mixed up together. Okay, so when we the scatter 1, 2, or 3 scattered around here, but if the rank is very small, then it means maybe one is located centered centered on this group. So here 1, 1, 1. That's why this value is small. And for this one, it means the 4, 4, 4 at high value is like that. So then that's the RJ. So when you look at the RJ, you can sense what's gonna be happen. Okay. Now then we have we using the same the formula here. So we are familiar with this one. Okay, then this one is a 4 and minus 1. So our chi-square value 30.32. So the degrees of freedom is k minus 1, 3 degrees of freedom. So XR is 30.32. So we go to the chi-square distribution table, where does this 30.32 does exist? Okay, we have to check it. Let's go to the chi-square table, which is familiar to us, then easy to calculate, determine whether significant or not. The last one was the spearman's rank correlation coefficient. We did calculate the correlation coefficient on the parametric distribution. That's what we call the Pearson correlation coefficient. The Pearson has developed how to calculate the correlation coefficient there, but this one is where Spearman has developed a correlation coefficient for the non-parametric approach. In that case, obviously, we use a rank instead of real data, original data. We transform every value as a rank. So we call it Spearman's rank correlation coefficient. Okay, so the data is I'll show you data later, and in next slide. The assumption is we assume that the sample available for analysis is a simple random sample, and that both x and y are measured at least the ordinal scale. So hypothesis, E is output and age. Okay, E is output, age. So with the two variables, one variable is E is output, and the other one is the age of the patients. So here the null hypothesis that they are mutually independent. Each independence means so that they don't show any trend, okay? But alternative hypothesis, there is a tendency for EEG output to decrease with age. So age is increasing, then EEG value may be decreasing, okay? Alpha is 0.45. Then how we calculate the Spearman rank correlation, okay? There, the correlation coefficient. Here, subject number, we have 20 subjects, And based on this one, we put the x value is age, okay? So the second one is the second value here. For the first x variable and y variable, okay, we have two variables here, the EEG value and the age, okay? Based on this one, we put the rank. 1, 2, 3, 4, 5, 6. Maybe this is the age, okay? It's age for them. And this one is the cardiac output, okay? So the EEG value. So lowest value, highest value. If this one is the one means the youngest one. If youngest one has a smallest EEG, and second one is a second EEG, then obviously correlation would be 1. Okay, but this data a little bit mixed, so we cannot figure out whether what's happened. But anyway, in that case, maybe we can sense the rank is located here. Low EEG seems to be here. Okay, there's a higher age group, and this one seems to be the high value for the EEG is located in the young age group. Okay, then but there may be some have the tendency. Okay, that's a kind of sense before analyze the data. But anyway, we have the rank here, so we look at the difference between rank. Okay. So y minus 18 is minus 17. In this way, we calculate the difference for the age, so the difference for the rank, okay? Then we put a scale value for this one, okay? This di square. Then finally, we're adding up all the rank value. 22,340 is our the statistic here. The hypothesis X and mu are mutually independent, and the alternative hypothesis not mutually independent. So we can have we can develop three different hypotheses schedule here. Okay, and what is the procedure? Procedure is like this: hypothesis testing procedure involves the following step. So we already seen how we look at seen the procedure. The first one is rank the values of x. X is first variable from 1 to n. So it's since n cases, n people's there, and for the I same rank here. Okay, so compute the di for each pair. Di is the difference between two ranks. Okay, for each individual. Then scale the value of each di. Compute the summation here. Do you remember this one? Okay, so after you calculate this value, put here. That's the formula. So RS is the spearmint rank correlation coefficient. Subscript S stands for spearmint. Okay, R is computed from Spearman's the nonparametric correlation coefficient. So this is the formula. Okay, so we know what is value. Then we can calculate this one very easily. Okay, then we move to next slide. If n is between 4 and 30, okay, then compare the computed value RS with the critical value R. So each one is appendix P. We have go to appendix P for the two-sided test. H0 is rejected at the alpha significance level, RS greater than RS star. Okay, RS is actually our calculated value, and this is from the table. Okay, from table P. Okay, so that's blah blah. Okay, they compare them, and if n is greater than 30, okay, the case is greater than 30, then we can transform this RS data using this formula. So transform into Z. Okay, when you get the Z value, then obviously we go to the standard normal distribution table. So going to this value where it's located here, then we can calculate the probability. But we have, if we don't go to the standard normal distribution table, and we have to use table P, then so we have T value here, then we get the cap T. Okay, it's kept here. The following correction for this one is for the tie. Okay, when the number is tie is large, then following correction tie is here. Okay, then we have a small number as a tie, we put the tide value, okay, equal rank, okay, instead of giving them to different rank, okay. This is for the tide value. But anyway, the T is the number of tide observations, okay. The RS our calculation, okay. For the RS we put the x squared, sum is the y squared and y squared and minus the value and blah blah. It is from actually the formula from 13.10.1 and the equation here r squared. Then how we calculate x squared? Okay, how to calculate y squared? That's the formula for this one. Okay, so when obviously when the sample size is increasing, okay, then there must be some tide value. It could be tide value. Whenever you have tide value, then some of the values t for the various tide ranks with x, and t this for the y. Okay, what if we do not have a tide value? Then this one disappears. Okay. Then most authorities agree that unless the number of ties is excessive, the correction. So if too many ties, then the data doesn't show anything actually. So the correction makes very little difference in the value of the RS. Okay, the number of ties are excessive. So it is not bad data, not to use them. Okay, we can measure them again. So when the number of ties is small, then we can follow the usual procedure of assigning tide observations, the mean of ranks, okay, for each via tide and proceed with steps 2 and 6, okay. Then based on this one, we calculate the correlation is this. We go to with this one. So unless with the less than critical value, then reject the null hypothesis. Okay. So our calculation 0.06 is less than this. This value is from the table, and then we can say the p is 0.001, so it's significant. Okay. Here the value is critical. This is the p value. So we have 20 sample sizes. Okay. Then 0.001 is this value, okay. 0.05, 5% is this value. This value is greater than within this range, okay. Under this point, then it's going to be significant. So value is getting smaller. Is exceeding this one this way, that is not significant. Okay. Then also the result for the Spearman rank correlation coefficient. Again, to get memorized that we have parametric distribution and non-parametric distribution. All the parametric method there is an equivalent to the parametric distribution, very similar one. But repeatedly saying if you can get the result for the parametric data, so you can figure out what is the population distribution, then you better use this one, okay, not this one. But sample size is very small and the population distribution is not determined, then you go to non-parametric test. Okay? Okay, that's all for talk today. Thank you very much. And we'll talk about some statistical method used in epidemiology in next week. Thank you very much.